Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Keith Kaplan, a software architect at Microsoft, and I'd like to welcome you to Behind the Code. In this series, we feature Microsoft employees who have achieved great things. Our goal is to reveal what it takes to create great software as we look at the technology and the person behind the code. Rob Short is an operating system pioneer. He helped Microsoft transition from the 1980s with DOS and 16-bit Windows into the 32-bit world with Windows NT in the 1990s. More recently, Rob was part of the team that further enhanced Windows to take advantage of the 64-bit processors of the new millennium. Today, he is the Vice President overseeing development of the Windows kernel and virtualization technologies. Please welcome Rob Short.
Thank you, Keith.
Welcome to the show, Rob. Thank you. When you were a kid, I think you did some things with radios and things to bug the neighbors. Is that true?
I never did them to bug the neighbors, but they did end up bugging the neighbors.
What was that?
We built a radio transmitter very early on, and we actually got to the stage where the police came with direction finders trying to figure out where the interference was coming because we were fairly close to the airport. And whenever we tried this transmitter, the neighbors' televisions all went bonkers. And it turned out that the police didn't have to use the direction finding because one of the neighbors was able to say, I bet it's one of those shorts down at the end of the road with a giant antenna hanging between their trees.
And you said we made this radio. This was you and your
My
brothers?
older brother.
All right. And eventually you went on to study something related to this in school. Is that right?
I studied radio and telecommunications.
And where was that?
In what's now Cork Institute of Technology. And I had a plan. I was going to work on radars, which I thought were the most fascinating thing, but unfortunately I couldn't get a job in radar, and digital equipment came and hired everybody in my class. So without actually thinking about it at all, I piled in a bus and went and interviewed there, and they offered me a job, and I took it.
What was your first job with digital?
My first job with digital was actually testing computer systems. It was PDP 1105s. Which was the first computer I ever learned. I actually understood how it worked. And what we do is we got these machines, they were almost always broken when they came off manufacturing lines. And we ran them through a set of tests and then debugged them and fixed them. And that was my first job, and I just couldn't believe anyone paid me to do this.
Was this the first time you had really worked with computers?
It was, I had learned about programming things, but it was the first time I'd actually touched one. And, you know, computers used to live behind glass walls back then. And these were real things, and you could sit down and play with them. In fact, it was in a manufacturing facility, and you were supposed to be clocked in. And we found several ways where you could cheat, and you could actually stay after hours and play with the computers when you weren't getting paid for it.
So it's cheat in the sense that you wanted to do more work than you were supposed to?
Yeah.
All right. You did do some other hardware jobs at Digital as well. After your technician job, you went on to...
Oh, I did a huge variety of things at Digital. One of the most fun things I worked on was I actually worked on manufacturing equipment for several years, about 2 years. And those things were actually driven by a PDP-11, but they were automated assembly machines. So it was a machine that actually would pick up parts. It would select a part, pick it up, stick it in a board, chop the legs off it, and actually test the part sometimes. And those things are computer-controlled, large mechanical pieces moving around. And I worked on, first of all, I worked on just setting up some of them, and then I worked on programming them. And one of the first programs I actually wrote myself was actually written in COBOL, if anyone here is old enough to have written anything in COBOL, but that's what we used to run on the PDP-10. And the setup on these machines was really complicated. So there was a whole collection of parts that you had to fit into the machine. There are dozens and dozens of parts, and you set these up into these racks, and you had to sort of thread them in, and there was an operator who set this up, and it took probably half an hour to set it up. And each different module, these are big things about the size of motherboards today, and they had a different mix of parts.
Right.
And it occurred to me that they were just building these basically the way the manufacturing flow of work went, and nobody had thought through how to optimize the flow of work, so you had to do the minimum amount of setup on the machine.
So once you've loaded up this machine with certain parts, you might as well make several of the things that use that
Right,
part.
or you might make the next board where you had the minimum number of changes. So we wrote some programs, I wrote myself, some programs in COBOL that would figure out which was the best optimal mix of things to put through these machines. And that was actually one of the most fun things I've ever done. I mean, I can look back at that and you could actually see it improved the flow of things through manufacturing.
You can actually watch more machines coming out of the factory every day this way.
Right, and the thing that was funny then was the manufacturing people and the engineering people were very, very different. There were people who were process engineers who actually, some of them were completely brilliant, but they didn't understand what you could do with a computer, even though they were building computers. And we started using more and more computers to run through the flow of things in manufacturing, and that was just an absolute blast. And I discovered some interesting things about that. I had a bug one day. We were trying to do this thing to optimize how you could put parts into a board that was slightly skewed. And there was a device that scanned the board, found out that the holes were off a little bit, and you used coordinate geometry to calculate where to put all the other things. There was a slight skew in it. And I had a bug in that thing. So this machine, a very, very expensive machine that ran 24 hours a day. And I got the thing wrong, and the table goes flying across, the head comes down, and giant bits of mechanical stuff, thousands of dollars worth of parts go flying in all directions.
Just a simple math error where it came down in the wrong spot.
Yeah, it was just a very, very simple bug, and you look and say, wow, there's an interesting impact from a simple bug. And the manufacturing guys are flipped out completely. There's thousands of dollars worth of damage, and this is in the late 70s, and the parts were actually fairly scarce. And they're all precision machine tools, and things just blew up, basically.
So it wasn't just a matter of going into the closet and get the spare one that's just like it.
Yeah, but when you have a machine like that that's down and it's not running, the manufacturing people get kind of freaked out as well. There's someone trying to run this plant 24 hours a day, and you've just smashed his machine. So there's an impact from bugs. And it wasn't just like we do today, just rebuild it and stick it in there.
We'll try again, we'll reboot.
This was a real bug.
And you did eventually go on to design some number of network interfaces and things there?
I worked and designed several different ways. The funny thing that happened in digital in Ireland, this was in Galway in Ireland, was one day one of the designers came of one of these PDP-11s, and I met him, and I had never met anybody that smart in my life. So I followed this person around like a puppy dog. And I brought him to the local bars in Ireland, and we drove him around the place, and then he sort of ran a course on how these things worked. And when he left, he very casually said, hey, if you want a job in the States, send me a note.
And who was this?
A guy called Bob Armstrong. He was the designer of the 1105 and 1134 and 44 series of mini computers. They were phenomenally successful computers. So I sent him a note, and ended up doing an interview with some people. But the thing that was hilarious was when I arrived, the project that he had invited me to work on was actually getting cancelled.
Did you still have a job at least?
No, I got introduced to a different crowd of people which I interviewed with. We're building a machine which became known as the VAC 780. And that was just an amazing opportunity. I had no idea. I just walked right into one of the sort of top projects in the world.
Just by happenstance, because
totally by happenstance. And I just lucked out working with some of the best people you'll ever meet. And I ended up working on that sort of as more or less an engineering flunky, and working for some brilliant people. And I did that, and I ended up taking over the engineering support for that when the team moved on to something else, and I spent about a year. One of the things at DEC was they liked people to work on support and supporting a product before they'd allow you to start designing things. And I worked on support for about a year, doing things like fixing, basically what we would call, DCRs, and understanding why the thing was failing in the field. Back then, if one of these VAXs was failing once a month, we would actually send somebody to go try and figure out why it failed once a month. And I worked on that. And that was actually very, very eye-opening, understanding what the computers did, what the customers did with the machines was really interesting.
And you had to actually go visit the customer and see the computer installed?
We'd go visit the customers, understand what the problems were, try and figure out what the problem was. And then that's when I started working with the software side, because it was always running the operating system, which was VMS. And the failures would be hardware-software combinations of things, usually, if there was a failure that required someone from engineering to show up. And somewhere along there, I started spending a fair amount of time digging into how VMS worked, which was the operating system. And VMS was a very, very sophisticated system, but it's really small compared to the one we have today.
And this would have been around what time? Sometime 1970s, maybe?
78, 79.
All right.
somewhere in there, that kind of time frame.
Having certainly done both, are there any comparisons you draw between designing hardware versus designing software?
It's the same basic skills are needed. The hardware people tend to be more disciplined than software people because the cost of errors is so high. Particularly, we built a series of chips. In fact, we built some chips at Microsoft. And the chips that I worked on, it cost you maybe $1 million to go build the actual physical part. So you did the design, and then you would send the design out somewhere. They make the masks, and you send $1 million. And it also takes a few months. And if you've a design error in that, it is unbelievably visible.
And you've just wasted several months and $1 million.
You've wasted several months and $1 million. And people don't think that's very funny. So you tend to be much
This
more...
audience finds it funny.
Yeah, they probably do. But people are much more disciplined about doing upfront design, figuring out how you partition the design, and figuring out how you can actually test and verify the design, because the designer is responsible for making sure the design works. And you can't say, oh, the test guys didn't find it. We're terribly sorry. We have $1 million piece of silicon that doesn't do anything.
What led you to try your hand at management?
Gee, that's an interesting question. There have been several times when I've transitioned from trying to be an engineer to being a manager. I ended up leading some projects several times over the years. And when you're designing something and you're working for someone, and particularly if you're kind of naive and impatient, you know that there's a way of doing it better than whoever you're working for, depending on who the people are. And I worked on one particular project, they're leaving some names out of this, but I was convinced that the manager wasn't as good as he should be. And I went to his boss and said, you know, this guy is really screwing up and we need to, get this project moving and I'll take it over for you. And naively, they said, fine, if you want to run that piece, we'll let you run that piece. And that was an eye-opener for me because I didn't understand all of the different aspects that were involved. And that project went fairly successfully. I had about 6 people working for me, and I would do things like call them up at 9 o'clock at night and say, where are you? What's going on around here anyway? And why is nobody working on this project? And I thought it was a blast of a project. And at the end of that particular project, we all went out to the bar that was in Tewksbury in Massachusetts. And we had a couple of beers, and we were talking about something, and one of these guys said, we want to tell you something.
And what was it?
And he said, we thought this was an interesting project, but we've decided none of us will ever work for you again.
Did it have anything to do with the 9 o'clock phone calls?
Yes, it had a lot to do with the 9 o'clock phone calls. And whether or not people, like, the only thing in their life is working on your particular project and whether they want to put up with that all the time. The other thing that you need to learn, I guess, at that time I had no clue at all about giving people things and letting them own it, right? So if I didn't like how something was getting done, I would just go change it. And that was sort of a combination of, it was a hardware project with a lot of code written in a PDP-11. There was an embedded processor that was controlling it. And if I didn't like things people were doing, I would just come in at 4 o'clock in the morning and redo it.
All right.
And I didn't understand how good that was at building a team. And there's way more leverage in having people working for you. And there's several times I did that there, and then I led something that actually worked after that, which went fairly well. And then I went back to being an engineer when I moved out to Deck West in Seattle.
All right. And
I worked on the processor design for one of the microvaxes that we built jointly with Dave Cutler. I mean, I worked for Dave, and we built this microvax processor. And I went back to being an individual engineer there because I thought that was going to be more fun. And as that team grew and some people left and moved back, I ended up running that team. And that was kind of fun. A little bit of history at Microsoft. I was running a fairly large team, somewhere in the, I guess, mid-90s. And I decided I was sort of burned out and I needed a break. So I took a few months off, and then I started a new project, which was the cluster Wolfpack project. Mm-hmm. And I said I was going to work on that. I was going to be a real engineer just like everybody else. And we hired 4 people. And I guess I was one of those with 3 people working with me. And we did a bunch of design. And I did just fine working on the design. and had a really good time designing the thing, reading specs. We did a lot of work reading and studying distributed systems, and we had fantastic design reviews with all the specs and everything, and then it came time to start writing code.
All right.
And I said, I'm going to write code just like everybody else. And
at this point, you hadn't done this for a little while?
I hadn't done this for quite a while. I'd been running a team of about 200 people. And you get to be sort of looking at the design and things, but you don't get to be in the code all the time. And there were a few people, Rod Gamache and John Vert particularly, who had been writing code every day for 10 years or something at that stage. And I would write a little bit of code and I would get it working, and they would write a lot of code and have it working. And I realized very quickly I was just totally outclassed, and I needed to either be able to catch up with these people or I needed to find some other way of adding value to the project.
But you say that you don't spend time in the code. I've been in your office. You do actually have an enlistment in the Windows source tree currently, don't you?
Yes.
So
but
you're
that's
just not actually writing code.
Yeah, but if you're going to manage a large team and you want to actually know what's going on, one of the best things you can do is watch the rate of change of code. And for probably 10 years, I walk into my office in the morning and I go and I type whatever. It's SDX sync now is the term, but it used to have slime incantations, and you said sync or sysync. And just watch the stuff that goes by. And you kind of go, why is someone changing that? Mm-hmm. And then you kind of go look at that, and I don't understand an awful lot of the details of this stuff, but I suddenly see, gosh, that's a really scary looking change that's happening in the memory manager. Not to pick on anyone.
Right.
And then you kind of go and you just drop into someone's office and say, gosh, what's this? And at least that way, you get to know if the things that you're seeing go by on PowerPoints or on the project schedule are in sync with the things you see happening in the code.
Well, that certainly ties into a question I wanted to ask, which was how technical should a manager be? You say you want to keep track of what the components are, but certainly you're familiar with what a memory manager is and what it does. And
how technical should a manager be? It depends on how technical the stuff you're trying to manage is.
All right.
The most important thing that a technical manager can have is an understanding of who knows what they're doing, right? You do need to know who the people are, and you need to be technical enough to know if somebody knows what they're doing. And the stuff we do, the kernel technology and the I/O stuff that I've spent a lot of time on, is quite intricate. And you get into a situation where people believe they understand it, but they don't understand all of the complexity. And as a manager, you need to understand who understands the complexity and who doesn't. And then that way you can help get people, the right people working with them, or you can get involved and change their assignments or whatever. I do think you need to be able to understand the top level design. You need to be able to understand if the design meets the requirements at the very top level. And is this actually a good design? So you need to be able to look. I spend most of my time at the higher level design and talking to people and understanding how the thing goes together rather than in the details of the code.
Rob, I know you took the job at Digital before you finished your bachelor's degree. Did you eventually go back to school?
Yes, I did. It's kind of an interesting story because I went back to school at the university. Well, I took a lot of classes actually at Boston University when I was living in Boston. And when I moved out here, I went back to the University of Washington and I did a master's degree. And they did not have the evening master's program at the time. So I signed up to do it during the daytime. And at that time, I was leading a project. I was working directly for Dave Cutler, who's not necessarily the most mellow of managers. But I did get Dave to buy into the notion that I would be heading over to the university and taking classes. And I was a pretty confident person. I've learned a little about that since. But I signed up to do this program, and I was going to do 2 classes at a time. And the first classes I signed up for were networking and data structures. And my very first day over there, I was in a class with a bunch of people that were much younger than I was. And they'd all just finished their bachelor's degree in Stanford or wherever they came from. And the instructor walked in and handed out a sheet of paper that was a test so that he could gauge where everybody was. And the math on this test particularly were like hieroglyphics to me. I stared at this and said, I am doomed. And luckily, I ended up meeting an Irish person that was actually from fairly close to my hometown in Ireland, who was Anne Condon. And she was finishing her PhD. And I said to her, I'm doomed, I don't understand this math. And she looked at it and said, I don't see what's hard about this, and started just explaining it as we walked down the hallway. So I ended up having Anne as my math tutor for a while. And I learned a lot at the University of Washington, but it was much, much harder than I had expected.
How did you decide to leave digital?
That's an interesting question. We had a site here in Washington, which Dave Cutler ran, and we were designing processors and software and hardware and software together. And we thought the VAX architecture was getting near the end of its tether. All the fuss at the time was about RISC. And we decided we would build a RISC architecture and a machine. And Dave led the effort across the company to define this architecture, which we called PRISM. And somewhere along the way, the company decided that they didn't have enough money to fund everything, so they just cut the funding for this and told a gang of us that our jobs were now going to be in Massachusetts.
And that your project was canceled?
Your project is canceled and your job is in Massachusetts. And I didn't particularly want my job to be in Massachusetts, so a few of us got together and said, well, what we should do is we should start our own company. And in the middle of that, Bill Gates called Dave up and asked Dave if he was interested in coming to Microsoft. And I guess Dave and Bill had a couple of meetings. And then one evening, Dave called me up and asked if I wanted to go meet with the Microsoft people. So I came over, 4 of us came over and met with Bill and Steve and Nathan Myhrvold. And we had a fascinating conversation all evening, basically. It started out, we were going to meet for an hour, and then we stayed there very, very late talking about what would a new operating system be and what could happen PC hardware over the years. And what could we do to influence PC hardware? Because we were very interested in computer architecture and hardware design, and I thought the PCs at the time were, fairly unsophisticated, and we could do a lot of work there. And, we went away from that conversation thinking, wow, these Microsoft people are much more interesting than we had imagined. And then I came and met several times with Nathan, and Dave decided that we should give this a shot. So.
And you say Dave decided that you had already decided that wherever you went, you'd go as a group?
Well, if there was a job, working with Dave is one of the most amazing things you can do. The guy is very, very pushy, but he's positively brilliant. And if you work with Dave, that something's going to happen, right? Maybe good, but may not be good. But I had decided that I would actually, follow him and work with him. And a group of us came and started what became the NT team. And at that time, I started a group to work on the hardware and work on sort of architecture of where the hardware meets the software. So we worked on that kind of stuff. And Lou Perizzoli was the leader of the software team, which Dave was obviously in charge of the whole thing.
Ted Cummert joined Microsoft during the early days of the NT project, and I talked to him about why it is that someone with your hardware background ended up at a primarily software company like Microsoft.
So early on when I worked for Rob in the early 90s, we were a small hardware team. Not many people know this, but when we were building NT, we were also building systems at the same time. So we had well-architected hardware systems that we were designing in tandem with this new operating system. And we had this very small team that built several actually complete computer systems, one of which is sitting right here next to me, the original motherboard, MIPS motherboard that ran NT. In terms of Rob's leadership of the team, we were a very small team. He was our bridge to the outside, as well as being someone who continued to contribute technically. And that was another thing that I noticed about Rob and that entire group of people, was how hands-on they were and how much they were involved in doing the work, as well as doing the things that they were doing in terms of leading the team and the projects.
What became of that hardware that you designed then?
That particular one that Ted mentioned ran almost all the 7-Elevens in Japan at one time. If you went to 7-Eleven and you bought a bottle of soda, someone scanned it, and it went into a MIPS machine running NT and went back to wherever their database was and ordered up another can of soda and sent it to that 7-Eleven. We built those machines. They were at one time, the MIPS machine we had was the fastest thing by a long way that we ran NT on. But it wasn't fast enough to make the economic advantage for someone to really take the risk and go out and buy a lot of them.
Except for 7-Eleven in Japan, evidently.
Well, NEC did a very good job of building some machines and of selling those to NEC customers, but over time, they actually replaced those machines with x86 machines because the larger company, Intel, had enough money that they had multiple different processor efforts going on at the same time. And they did an amazing job. The early Pentiums were, each of them doubling in performance, and they were able to do that and outrun the other guys very, very well. And I know the people at Intel very well who were designing these chips, that they're smart people. And it wasn't based on the instruction set. It's a broader problem than just the instruction set.
It's just how well they implement it.
It's how well you can do it, if you can have multiple design teams, if you can have really good analysis tools. Intel had the best fab technology. I haven't been tracking it as well, but they had by far the best fab technology. They had the best simulation technology. Your ability to get the chip working first time, meaning this time to market advantage. And they had a phenomenal testing methodology. So they moved very, very quickly. And I personally demoed one of the MIPS machines with a graphics accelerator that we designed and built, and I demoed that to Andy Grove.
Who at the time was CEO of Intel.
He was CEO of Intel, and he came when Bill brought him into our lab, and they stood there, and Andy watched it for a minute, and we demoed it against an x86, and Andy just turned around and walked away. But I thought, he didn't say very much. And I found out later from some friends of mine who worked at Intel that he actually said a lot.
He's just not in your presence.
He went back to Intel and said, we need to wake up.
And you just mentioned the importance there of good simulation and testing tools, and I know that's something that you've also sort of led the investment in the Windows team also, and things like the driver verifier. And
I've always been interested in testing. Working on hardware, working in a manufacturing facility, it's interesting to see how far down something can get and find a bug in it, because the closer to the assembly or the closer to when you write the line of code that you find the bug, the less it costs. If you take a computer and you ship it off to somebody and they're in Yugoslavia or someplace and there's a bug in that thing, it's incredibly expensive to fix it. So I've always been interested in testing and trying to figure out how you get things a little bit better. And one of the huge problems we've had in Windows is we write a small number of drivers here at Microsoft, and there are approximately 100,000 or more drivers that people load into Windows. It runs in the same address space as everything else, and if that driver has a bug in it, it corrupts something somewhere in the system. And we started an effort, which I guess I funded in right around 2000, to try and improve the quality of drivers. So we started both looking at the drivers from the point of view of why are we seeing failures, what are the failures, catching the crashes, having them come back to Microsoft so we could look at them and understand them, and at the same time trying to figure out what are the common bugs that people wrote. So we had some people here build a thing called the driver verifier, and what that does is for one simple example is if you allocate a piece of memory, and one of Mark Lakowski's tough interview questions were, if you allocate a byte of memory, how many are you allowed to use?
I think the answer is 1. Luckily, he didn't interview me.
He used to say half the people that work here don't seem to know that. But one of the big problems you have is people allocate memory and then they write before or after that piece of memory because of some assumption that's made somewhere. So what we did in the driver verifier, and this thing we call page heap, was we put the pages on either side of the thing you've allocated and make them inaccessible, so that if you write over the edge, you get a fault. And we started looking at that, and there was a few people, Landy, Sylvie, a bunch of people worked on this thing, and we kept putting in new little tweaks. Every time we'd find a bug in a driver, we'd say, can we catch that in driver verifier? And you can run the machine with the driver verifier, and it finds a huge number of these common things. We found a lot of the problems that way.
And these would be bugs that maybe had always been there, but that you sort of get away with this bad behavior 99% of the time.
Yeah, a lot of these bugs are bugs that were there, but corrupted somebody else's memory. So maybe you get the wrong answer in Excel or something, and you think Excel is giving you the wrong answer, and in fact the driver is trampling on a piece of memory somewhere. that it doesn't own. And we found a lot of very interesting ones. One really interesting story is we have the OCA, which is the online crash analysis tool.
And this is the little thing when you get the pop-up that says, this program has crashed, would you like to send a report back to Microsoft?
Right, and you send a report back to Microsoft, and that dump ends up on a server at Microsoft. And we have tools that analyze that dump and try and make a best guess of what might happen and put it in these different buckets. And the person that leads the effort analyzing these things, what we thought we'd do was we would take a sort of an engineering approach and try and figure out if there were categories of things that failed, and then go after those failures and say maybe we could change the design of the driver, change the tools or something so we wouldn't see more of them. And we found one particular crash that was happening a lot. And we tracked it down. It looked like a single-bit memory error. And it was tracked down to being in an audio driver that came from a different outside company. So we found this, called the company up, talked to them, explained where the problem was. And what it was in an error path. They were setting a status bit, except they had gone one over the end of where the ERP is, and they're setting the status bit way off into random memory that's down beyond the data structure they own. So we fixed this, and we were all feeling very good. And a couple of days later, Vince Orgovan shows up and says, boy, this looks like exactly the same crash, but they don't have one of these audio drivers. They have a different audio driver. And one of the things that we do in the crash analysis tool, we look at the crashes, and we put the crash in a bucket, and then you can, because we have a lot of crashes coming in, you can say we've never seen this crash on a machine that didn't have this type of hardware. So that allows us to associate the crashes with the hardware. And so we look at this, and we find a different company's driver has exactly the same bug.
A strange coincidence, it would seem.
A strange coincidence, perhaps. So we go and say, gee, did we ship a sample audio driver? So we go look at the sample audio driver. There's the bug.
So I know you've also been very outspoken in favor of sort of architectural discipline and having, well, what you would call architecture. What does architecture mean to you when you say that?
It's true I've been outspoken. It's not true that I've solved the problem. We've tried hard. To me, architecture means the top-level design. And if you think about the architecture of Windows, Windows is an enormous thing. There are a lot of different pieces in it. And we think of the architecture as the overall form of that system and how the pieces fit together. And making sure that when you add a new piece, that it fits into those pieces in a structured, well-thought-through, designed way, rather than some little poorly thought-through thing. And we do a good example is just thinking about building architecture. And the weird thing, I picked up some paper from the Harvard Business Review, and the opening line was something to the effect of, a $100,000 house is never started without a detailed set of plans and architecture, yet multi-million-dollar software projects are routinely started without good architecture. And one of the examples I use is you say, you're going to build a house. And well, you're going to need a whole bunch of 2x4s nailed together, so why don't you have someone drop those off and have someone start nailing them together, and you can do that in parallel with doing some of the design. Mm-hmm. And that might sound completely absurd if you think about doing it in a house, but you go talk to some of the teams and they say, we're building one of these, and I thought I'd code this little piece up because it sounded like, something, we're going to need one of these anyway.
It's a prototype wall, perhaps.
Yeah, it's a prototype wall, perhaps, exactly. But as Windows grew organically, and it did grow sort of organically, the team's very large, there's a lot of parts in it, very, very complicated interactions. There wasn't enough thought into the cost of each of these features on the overall whole. And particularly because we have a culture here where most of the people we hire in Microsoft are very high energy people, and they're determined to succeed. And their view of succeeding is, I got my piece done, a lot of the time. And so they're going full speed ahead, and they're going to get their piece done, and some other team isn't helping or is perhaps perceived to be in the way because they're also trying to get their piece done full speed ahead. And people make localized decisions that aren't necessarily in the benefit of the whole. And sometimes it is better to have the system perform perhaps not as good as it possibly could and leave it so that it's extensible and maintainable and understandable. So, doing a good job of the top-level architecture is really important.
What traits do you think successful architects all have in common?
Whoa. I'm not sure all the successful architects have traits in common. If I think about what it takes to be a successful architect, you need to be able to think about a problem both abstractly and understand what the details might mean to the design. And if you think about that in terms of buildings, you need to be able to understand the abstract view of what a building is like, what the spaces will be used for, at the same time as understanding the impact of the building materials. Some things you can build with a very narrow wall, some things need a wall that holds it up. And it's the same in technology, so you need to understand sort of the very top level goal of the design and what the interconnections would be. But you do need to understand the details, because if you ignore the details, they'll come back and get you later. Key attributes that I've been looking for in architects, and we've gone very much out of our way to get people that are quite different with different backgrounds. I want people who know how to listen, because otherwise you can't understand what someone is trying to do. You need people who think very, very carefully and broadly before giving an opinion. One of the problems we've had is having consultant kind of people who, give a sort of criticism of a design very, very quickly, and then that backfires on you, and people aren't interested in your opinion if all you do is insult their design. So you need people who are a little bit calm, can actually help. So I guess the ability to look at the design abstractly, understand some of the details. You don't have to understand all the details. You need to be able to partition things very carefully into layers in your head, and you need to be very good at listening and very good at writing. We need people who can write down their opinions.
You formed a team that we call the Core Architecture Team, or Core Arch.
We had the Longhorn project, which, I guess this is a public show. The Longhorn project did not perhaps go as well as it should have, to be politically correct.
Did it remain on schedule the whole time? Or?
It didn't necessarily remain perfectly on schedule. And there were some minor technical problems along the way where pieces of the design didn't work. So Jim Alshin drops into my office one day and says, gosh, we've got some large hunks of technology, and when we're trying to put them together, they're not meshing. And, you tried to do this architecture thing. Why don't you go think about it and figure out how you could actually do this? Mm-hmm. So I went back to Jim and said, I'm not going to go and have like a group of people having nice meetings with each other anymore. I'm not interested in doing that. So what we should do is we should get some people full-time. And what we want to do is get some full-time people who can look at the broad view of the thing. And then we want to get people appointed by their vice presidents to be responsible for the technology in their area, such that they could make a decision that would stick for that area. And we made a list of these people that we call the Windows Architecture Team. And then we looked at some of the very hard problems that were happening across the system and said, we need to get some of the core architecture people full-time on this, and representatives from the team as well, who would be the people from Windows architecture. And then we sat down with them and worked through some of the designs. And when we hit a problem where somebody wasn't agreeing or something, I would go back to Jim and say, Jim, you asked me to do this. We're doing this team isn't agreeing, and now I want you to use your influence as like the guy who pays their salary to tell them that they have to listen. And the good news about that is it actually worked, and we did solve some problems. The bad news is the way Microsoft works, you can't have the ivory tower guys just appear and come and say, your design is screwed up, you need to fix it, because those guys will never talk to you again. So what we've been trying to do is have a slightly different approach where we ask people to write architecture overviews up front. And we assign somebody from the architecture team. And if you want to design some new piece, you write down what you're trying to do. And we assign one of the people from the architecture team to work with you and introduce you to the different people around, because we have people who know a lot of people. So they can introduce you to the different parts of the system that you're going to have to work with.
One member of the core architecture team that you've worked with since the late 1970s at DEC is Daryl Havens. And here's what Daryl had to say.
Rob's a very unique individual in the sense that he can continue to follow all the technical things. And I think a lot of it comes from just his breadth. He was a hardware guy, he designed hardware, he worked on microcode, he worked on operating systems, he worked on software, he's done all kinds of things. And in some ways you never really lose that, and so he's never lost it. And I guess that Some people who really want to manage people and manage large projects lose that because they stop focusing on it. But Rob's in all the core arch meetings. When we do a core arch review, Rob's there, and he has input. Sometimes he does a lot of listening and then he'll make observations afterwards, but most of the time he's there and he's saying something. But at the same time, he can also manage the group, right? And I think he's managing the group more because we needed somebody to manage the group than he wants to be a manager or he wants to be he didn't want to be a corporate VP. He didn't want to in the first place, right? He got talked into it. But yeah, so I think that's how he manages to be able to do both.
Did you really have to be talked into taking a vice president job? Let's check Daryl on that one.
Well, we'll check Daryl on that. There's a piece of that that's true. There's a piece of it that it's kind of a nice honor to be a vice president of Microsoft, and I kind of look at that and go, whoa, that's kind of interesting. And, you get free clothes, nice T-shirt, it says Windows on it.
See, I had to pay for this myself, yeah.
Yeah, see, you get a nice free shirt and everything. I was actually asked if I wanted to be a distinguished engineer, if I wanted to be a vice president. And I said, I'm sort of psychologically a distinguished engineer. But at that time, I was running the driver team and a bunch of other things. And when you meet with people outside of Microsoft, it's much more influential to be a vice president than it is to be a distinguished engineer. And Brian Valentine was the guy who sort of gave me the choice and sort of put it that way. And then when you meet with people and you show them a card and say you're a VP at Microsoft, they might take the fact that you're talking to them to mean that something that you're signing up for is actually going to happen. Whereas if you're a distinguished engineer, they might think, you're some research guy and, you're not necessarily in a position to make a commitment. So that's how I ended up accepting that at the time. And I was a little suspicious of it. You've got this view of, VPs as being kind of stuffed shirt people, and I've tried very hard not to be one of those.
How do you divide your time today among sort of managing the project versus managing the people that work for you?
Time management is the single hardest problem when you're working on this stuff. You can use all your time on any of these problems. I could spend my whole time on architecture reviews. It is the most fun, it's the most exciting, most interesting thing. You spend your whole day at it, and at the end of the day, you've actually accomplished nothing except maybe giving people some feedback. So I spent a lot of time with a coach from the executive training people, and I got some very interesting advice. One is think about the value that you personally add. Where do you add value? And what are the things that you can do that other people perhaps can't do or aren't in a position to do? Mm-hmm. So you try and allocate some time to that. You need to think about what are the things you're trying to have happen. One very expensive thing is if you're trying to make something happen, people watch how you spend your time. So if I spend a lot of time with the architecture team, people think Rob thinks architecture is important. If I don't show up at any of the meetings, they think, oh, he didn't think the meeting on the transaction stuff was interesting, so he didn't show up, so transaction stuff isn't important. Not to pick on anyone, but just... Mm-hmm. So you have to actually look at, are you putting the investment in your time into where it can make a difference? What I did is I divided my time up, so I spent a third of the time on the architecture stuff, about a third of the time on the kernel and virtualization thing, and another third of the time on people. And I would sit down once a week with my admin, Katie, who runs my life, and we would sit down and try and figure out what all these meeting requests, which of the meeting requests you're going to accept, which fit into each of these buckets. And, really the thing that matters is people. And so you make trade-offs in favor of, spending more time with people. I do a lot of one-on-ones with people all the time. But managing the time is the hardest thing, because any one of these things can use all of your time. And, I learned some stuff from the coach people. I've learned some stuff from watching people like Bill and Steve, who have the most demands on their time you can imagine. Steve is incredibly disciplined on how he uses his time. And you watch that and you say, whoa, maybe I should try that. But then you also get in a situation where there's somebody that you know, or you like, or whatever, and they want, to meet and talk about something. And if you say no, they say, oh, this person's unapproachable. So you have to balance that fairly carefully. But it's very hard.
You've been on a lot of very successful teams over your career. What would you attribute that success to?
Part of it is luck. Part of it is choosing the right teams. I've also been on some disastrous failures. I've worked on some projects that have fallen flat on the ground, which has been an eye-opening experience. Most of the work I've done at Microsoft, I've done as a manager or a team leader. And we've been successful because of the whole team. I'm not the person who's written the most code around here. I've written a small amount of code compared to a lot of other people. The people I've worked with have been mostly phenomenal. And I've had people working for me who are just completely awesome. And it's amazing to come to work and say, wow, these people actually work for me and I can help them get things done. I mean, that's been the most exciting thing. So it's all people. It's all about having the right crowd of people. And really, as a manager, what you try and do is you try and get the clarity of what it is we're doing and make sure that we know what the team is actually trying to do. And I think I'm reasonably good at that. So you get the team focused, you get the team doing. But it's all about having the right team of people.
Now let's move on to some more fun stuff. What do you do in your spare time?
It depends. What time of the year is it? Where am I? I like to do outdoor stuff. Mm-hmm. More than indoor stuff, but I like to read a lot. I've done a lot of skiing, done some mountain climbing, water skiing. I've hiked on, I would say, most of the trails that are around Washington. When I moved out here first, I actually bought one of whatever those hiking trail books are, and I would open a new page and put my highlighter on it and go hike that trail and go after them one after another. So I've done a lot of outdoor stuff like that. I've tried various different things. A friend of mine once said, it has to say stupid, dangerous stuff, and Rob will sign up. So I've tried a number of stupid, dangerous things. I've done a fair amount of mountain climbing, but not necessarily in a dangerous way. Tried racing cars. I wasn't very good at that. The NT team as a group, after one of the releases, we all went down and took a class down at Laguna Seca, and we drove racing cars. And I guess I was in the middle of the pack. But just one of my favorite discussions about that is to show the concentration that some other people have compared to me. I came in and I said, turn 5 is really getting me, and I see people just going whizzing around it, and I'm having a hard time with it. And Dave Cutler says, I got turn 5 down. He says, you're coming into turn 5 and you drop the car down into 3rd, and there's a line on the asphalt. And I put the right wheel on that line on the asphalt. And when I get the right wheel on there, I get the throttle exactly right. Then you look across and there's a berm, one of those red and white stripy things, and I look at the 3rd white one. And I turn the wheel towards the 3rd white one, and I put a tiny bit of gas so you can feel the car sort of settle. And then I go to the 3rd white one. And then there's some trees over on the other side, some little bushes, and I aim for those trees. And I get around those trees, and right as I get right over to the far side, I put the gas on full, and I'm up the hill. And I'm thinking, my memory of this corner is going, whoa!
Rob, we have a few questions that we ask everyone on the show, and the first one is, what advice would you have for someone in this field?
I don't think the same advice goes the same for everybody. Different pieces of this technology are interesting to some people and different pieces aren't. I mean, I love the stuff where the hardware meets the software and it's intricate in a funny way. I think everybody going into the sort of anything to do with operating system or software should understand sort of basic computer architecture. I think everyone should take a compiler class so they understand compilers and how that stuff, that low-level thing before you work on any of the higher-level stuff. I think understanding that as a basis you can use for everything else. But my basic advice to everybody who's asking career advice is find the right people. You need to work with really, really good people. Don't make decisions based on technology unless you're totally addicted to something. I mean, you can say, I want to go work on video games, but if you're going to go work on video games, find the best people who will challenge you, push you, scary people that know more than you do, so that you can work with really good people. If you're with good people, then good projects happen. But, just picking something because of technology isn't always the right answer.
How would you describe your work to someone who is not technical?
The most interesting puzzle in the world. There are a couple of things I tell people. One is working on the operating system. I describe it as we build infrastructure, so it's kind of like sewers. They're like absolutely essential. But if you find out that the stuff is there, it means we've screwed something up. When you plug a little USB widget into the system, that should just work. But there's an amazing amount of stuff that has to happen for the system to know about that thing and to know there's a file system there. You should never, ever know that. So we build infrastructure. It's like the stuff that's buried underground, and it's there. I tell most people that I work on technology, but I tell people that it's just this amazing puzzle that you get to play with all day, and you get to work with amazing people who play with the same stuff.
In life, what would you compare to producing software?
Depends what you mean by producing software, I guess. There's lots of interesting engineering things that people are doing. I think medicine is very, very interesting. Some of the things people are doing in biotech are fascinating things that are related to, the same kind of puzzle or the same kind of interesting things. But I could think of lots of interesting engineering things that people are doing that would be similar to producing software. But I don't think there's anything that has as many degrees of freedom. If you're building an airplane or something, you don't have as many degrees of freedom. There's a basic shape, there's engines, there's things like that. Whereas software, there's an enormous amount of freedom. That's also the problem, right? That's how we end up with complicated designs that we can't figure out how to debug them.
You know you're a computer nerd when?
I guess one thing that people tell me I'm a nerd when I see something and my reaction isn't, wow, it's cool that it does that. My reaction is always, I wonder how that works. And I'm interested in knowing how it works and what the interior of it is rather than what it's doing. And I look at stuff that way. I mean, I talk to people about, wow, did you see this exciting new device that came out from so-and-so, and it's the easiest thing around to program. Stuff like that, I guess. It's a hard question to answer.
We'd also like you, Rob, to draw your favorite data structure and explain it to us.
I don't have a favorite data structure.
You were going to prove to us that VP didn't mean puffy suit, so here's your chance.
How do I prove that? He warned me he was going to ask me this. And the stuff that I'm interested in terms of data structures and things are all the things related to synchronization and locking and things like that. And I was thinking of trying to draw how push locks worked, but then I wimped out of that. One of the cleverest things I've seen in my career, and this is really old, is a thing called a VAX interlocked queue instruction. And what this is a way of sharing a data structure between multiple different machines. And I wrote the microcode that lived in the device that could also share the same data structure. And it was a hardware device that worked with in conjunction with the software, with the operating system, to share the same thing. And it's your very, very basic queue, but the interesting thing about it was built using relative offsets. So rather than having the address in the entry of the queue, it was a distance from where you are. And that allows two different processors to be in two different virtual address spaces and share the same queue. And the hardware could also come in and do it. And it was an interlocked operation, so the thing had to be aligned on a cache line. And so what you had is for the head of the queue, let's see if I can figure out so there's an offset rather than an address of the next entry in the queue, and the thing is circular. And I just think that was one of the cleverest things I've ever seen. I didn't design it. It was designed by some of the VAX architecture people, including Cutler. But the offset was your address plus the offset that pointed you at the next entry. And that allowed you to have multiple different processors all running different processes in different address spaces, talk back to the thing. So these are data structures, but these are just the headers. So you have an offset. My writing here isn't winning. So that offset will point back to the next thing, and then because it's circular, you can point it all the way back around, and there are backward links, but it looks something like that. I don't know if that means anything to you. But the thing that was nice about this was there was actually an interlock bit in it, and it was combined with the hardware, and the hardware had the ability to do a lock instruction. So a device can come in the middle of the processors talking to these things and pull things out of the queue or stick things into these queues. And this was something that was done in I don't know, 1980 on VAXs. The VAX CI, which was the cluster bus, was the first one of these. Then we built a thing called the DR780, which was a very high-speed I/O device that used these. But it's very, very simple, but very clever because it's completely interlocked.
And an example of why you might want this is now software could be queuing packets, for instance, and a network card could be taking them off the queue at the same time.
Exactly.
All right. Could you sign your name to your data structure, please? Hold it up for us all to see. It's a ritual, Rob.
It's a little messy.
Thanks, Rob.
I don't know. I was trying to think what to write, but I don't know. That's kind of a funny conversation.
We have time to take some questions from our audience that we have here today also.
Rob, you've worked on a lot of different projects over the years. Which ones do you think had the largest sense of mission felt by the members of the team, and why is that?
Several different things I worked on I thought had an amazing sense of mission. When I moved from Ireland to the US, the VAX 780 project I worked on had an incredible sense of mission. It was a relatively small team. There was new hardware and new software. And the attitude was, we are going to change the world by bringing this sort of mainframe level computing power to, to mini computer stuff. I worked on Ethernet, and there was a sense of mission there that we were going to connect all the things together, and that was amazing. The Microvax, actually, which was another DEC project, had a sense of mission. When I came to Microsoft, the NT team had an incredible sense of mission. And our attitude was we were bringing real software technology into PCs. And we were going to change the PC hardware so that we could make sophisticated multiprocessing. We were going to have a real, very, very sophisticated operating system that could go all the way from the desktop. So there was an amazing sense of mission in that. Windows 2000, when we did two huge things in Windows 2000. We put in the Active Directory and we put in the plug and play. And our team, I think, had a sense of mission because we were going to automatically configure things. XP, we were taking the NT code base and bringing that to consumers. And that was very, very clear. I think that the sense of mission there was amazing. The early Longhorn, the mission wasn't quite as clear. And that caused some of the interesting problems. I think Vista ended up having a sense of mission that wasn't there with the early Longhorn. But Windows 2000 and XP had an amazing sense of mission, and we knew what we were trying to do. And it makes a huge difference to the team.
Thank you, Rob, from the Technical Community Network, for being our guest today. And thanks to all of you in the audience for coming.